Hello everyone. Today we will learn how to apply the chain rule to derivatives. First of all though, what is a derivative? A derivative can be described as the slope of the tangent line at any particular point of a function, and is also known as the instantaneous rate of change of the function f of x at x. In short, this means that a derivative is the slope of the slope. Similarly, by taking the derivative of the given function, f of x, we can find the equation of the derivative. This process is called differentiation, where when we take d over dx of f of x, we will get the derivative, which is denoted as f prime of x. Let me turn that off. So, what does all that mean? Let me show a quick little example. Say that we have this function that curves like this, and we're looking to see what the derivative at this particular point is. Basically, it will mean it is this line as it goes along that point. This is referred to as a tangent line, and it is, as you can see, the equation of the slope at this given point right here. So, let's begin with some review. The chain rule typically includes lots of other rules you've most likely learned previously, but just in case, let's go through the main ones. To start with, the derivative of a constant is 0. So say we have the derivative of a constant c, it will equal 0. So for example, let's say we're taking the derivative of 2, the answer will be 0. Similarly, say we have to take the derivative of, let's say, 300 to the third power. That's kind of a crazy number, but luckily for us, we don't have to do any multiplication or anything because our answer is just 0, as 300 raised to the power of 3 is still a constant. Similarly, this also applies for any constants that are denoted with other symbols, for example pi. The derivative of pi will also be 0, since pi is a constant equal to 3.14 and so on. Similarly, when we have a constant in front of our equation, we can pull it out in front of our derivative. For example, if we have d over dx of c of f of x, we could rewrite this as c times d over dx of f of x. And by the way, this d over dx part is just to denote the fact that we are taking a derivative. So, an example of this, say that we have to find the derivative of, let's say, 3 times 2. We could move that 3 out in front. However, as we've seen before, this will still just equal 0, as 3 times 0 is 0. Next, let's look at the power rule. This is one we see all the time, and I'm sure you've seen already at some point. So, as review, the power rule is used to define the derivative of a variable to the power of a constant. To find the derivative of a function using the power rule, you multiply the variable, in most cases x, by the exponent and then subtract 1 from the exponent, which can be seen in this formula here. Let's say n is any number times x to the power of n minus 1, where n's are any constant number, like 3, 5, 6, 7, any constant number. And x here is any variable. This also works if another letter is used, say u, it'll be n times u to the n minus 1, and so on. So let's look at some examples of this. Let's say we're given the function x to the second power. How do we find the derivative of this? Well, the derivative will equal 2 times x to the power of 2 minus 1, which turns out to be 2 to the x1. And some teachers mention this, some don't, but anything to the 1 is just whatever it is. So in this case, x to the 1 is just x. Similarly, if we had 2 to the 1, it'd just be 2, as it is 2 times itself exactly 1 time, which is just the number. So the answer to the derivative of x2 is 2x. Now, let's say we're given the function fx to the third power. How do we find the derivative of this? Well, notice how we have a constant in front of the x to the third power. This means we can take it out in front when we write the derivative. Say we have d over dx, 4 to the third power. Well, 4x to the third power, sorry. We could rewrite it as 4 times d over dx of x to the third power. And now, remember that since this 4 is out in front, after we find the derivative of x to the third, we still need to multiply it by 4. So, using our formula, we end up with 3x to the power of 3 minus 1, which will equal 3x to the second power. And now, to multiply these two together, it'll just be 12x to the second power. Moving on. Other derivative rules can include exponential or trigonometric rules, which I will list very soon. I recommend pausing the video and noting down these somewhere you'll remember. As these are extremely helpful in future problems we have to work on. And I won't go through each and every single one, but I will go through the ones that we will be using later in this video. So let's begin with our exponential rules. How do we find the derivative of e to the x? Simply put, it's just e to the x, which is great. Now, how do we find the derivative of e to the kx, where k is any constant, say like 4, 3, 2, pi even, any constant? That just means we will end up with k times e to the x, or simply kex. Next, let's find the derivative of the natural log of x. This maybe surprisingly, will equal actually 1 over x. And for example, say that we have a function instead of just an x, that will mean our derivative will be equal to the derivative of the inside function divided by the inside function. And we will see why this is the way it is later in this video. Now, let's move on to our trigonometric rules. So, the derivative of sine x is equal to cosine x. Similarly, the derivative of cosine x is equal to negative sine x. About half of these will have negative signs in them, and afterwards I will show you a quick little trick to remember when and when not to put these negative signs. Next, the derivative of tangent x is equal to secant squared x. And let's go on to my next one, which is the derivative of secant x, which is equal to secant x times tangent x. Next, the derivative of cosecant x is equal to negative cosecant x times cotangent x. And finally, the derivative of cotangent x is equal to negative cosecant squared x. Now, these three with negatives, it might seem a bit random, but there are proofs for these, and a quick way to remember it is notice how all of these negatives coincide to the trigonometric functions that begin with a c. So in my brain, I remember if I'm taking the derivative of something that starts with a c, that means I will end up with a negative answer. But how does the chain rule relate to all this? For one, a lot of these rules are actually derived from the chain rule. And the chain rule is used when a function lies within a function, as is seen in this form below, f of g of x. If you see something like this pop up when you're taking derivatives, you know you gotta use the chain rule. Moving on. I apologize. This rule works by taking f of g of x and denoting f of u and g of x from the original function, where f of u is like the outside part of the function and g of x is the inside of the part of the function. And after you figure these out, you will then take the derivative of f of u and the derivative of g of x, and then they will be plugged into this formula over here. The formula for the chain rule is f prime of g of x times the derivative of g of x. Let's begin with some examples. As this sort of thing, it's much easier to see it when it's an action rather than me just telling you there's an inside and an outside, because lots of times it's a bit difficult to see at first glance what the outside and what the inside will be. So let's begin with our first example. Let's say the function we're given is y equals 2x plus 4 to the 500th power. Now, we could multiply this out and then take the derivative, but I mean, to the 500th power is kind of crazy. So, that would take forever. But luckily for us, this is where the chain rule comes in. So, when you look at this function, which part looks to be the outside of the function, and which part looks to be the inside of the function? Well, we can see that the inside is this 2x plus 4 right here. And we will label this as g of x is equal to 2x plus 4. By labeling this, we can now plug in our little u to this equation. Oops. And what we're left with is our outside function. So f of u is equal to u to the 500th power. So when you see anything to an exponent like 2x plus 4, 3x plus 8, anything like that to the power, you know that this power is the outside of the function, and within these parentheses is the inside. Now, how do we take these f of u and g of x and plug it into our formula? F prime of g of x times the derivative of g of x. Well, first we need to find what the derivative of f of u and g of x both are. So let's start with f of u. The derivative of f of u is equal to the derivative of u to the 500th power. Now, this goes back to our power rule that we saw earlier, where I'll rewrite it just in case. N times the variable to the power of n minus 1. In this case, our variable is u, so instead of x here, we will have u. So, to solve this, we will do 500 times u to the power of 500 minus 1, which turns out to be 500u to the power of 499. Now, we have to find the derivative of g of x. So, the derivative of 2x plus 4, at first glance, might be a bit confusing since it might at first seem like just something you have to know. But, in fact, the power rule can also be used here. And then also the fact that 4 is a constant, we can ignore the 4, as the derivative of a constant is 0. So when we look at this 2x, there's actually a little invisible 1 right there, which means we can in fact use the power rule. So the power rule states n times x to the power of n minus 1. So our power is 1, and 2 is a constant, so we can actually pull out the 2 in front. So it'll look something like 2, then we have 1 times x to the 1 minus 1, which ends up being 1, as anything to the 0 power is 1. And then 2 times 1 is 2. So let's rewrite all of this. F of u is equal to u to the 500th power. And we found that f prime of u, or the derivative of u, is equal to 500 times u to the 499th power. Similarly, g of x was 2x plus 4, and we found that g prime of x is equal to just 2. Now, let's plug this into our formula. Now, also, let's remember that our original equation was y equals 2x plus 4 to the 500th power. So, we use our formula f prime of g of x times the derivative of g of x. So, fu is first. We have 500 u 499. But this u, what do we do about that? Actually, as is seen in our formula, we put g of x here. So the first part will be 500 2x plus 4, which is our g of x, to the power of 499. And then we multiply that by g of x, which is just 2 times 2. Now, this may seem really complicated at first. There's a 500, a 499, an exponent, multiplication. However, this, and at least the work that we're doing today, all that is left for us to do is to simplify. And luckily, we only have to multiply out the constants, 500 and 2 here. So this will end up equaling 1,000 2x plus 4 to the power of 499. This is our final answer. Now that we've seen how this works, I guess with a quote-unquote regular problem, let's see how it would work with an exponential example. So let's say we are given y is equal to the e to the 8x power. Some of you might recognize this from earlier. However, we're going to go step by step and explain how you would work this using the chain rule. F of g of x times g prime of x. And some may notice I'm using derivative and prime interchangeably with each other, but they mean the same thing. Derivative of g of x or g prime of x are both the same thing. So, let's begin with e to the 8x. What is the inside and the outside function of this problem? Well, the inside at first may seem like it's the e, since, in our last problem, our inside was what was inside of the parentheses below the exponent. However, Notice that we have an e to the x where we're using the form e of x. And when you plug something into e of x, where do you plug it into? The exponent. So for this problem, the inside is actually the 8x in the exponent. So f of u will equal e to the u, and g of x will equal 8x. Now we just need to find the derivatives of these two. So f prime of u is equal to just eu. As we saw before, the derivative of e to and like the variable x, or in this case u, is just e of x. So next, the derivative of 8x. Like we saw in our last problem with the 2x, it's the same concept, where this 8 gets pulled in front of x to the first power and ends up being 8 times 1, which is simply equal to 8. And if you want to remember this, you can remember that any constant times x, or any single variable, like if it's 8 times u, 8 times y, as long as you're finding the derivative of d over du or d over dy, will equal just 8, as it will end up being 8 times 1, which is 8. So now that we have our f of u, g of x, f prime of u, and g prime of x, how will we put this into our equation? F of g prime of x times g prime of x. It's basically the same as last time, where we take our original equation, which was e of u, and I say original because the derivative is the same, but it would be, as is written, the derivative of the original equation with respect to u. So this will be e, and our u we plug in g of x for. So e to the 8x times the derivative of g of x, which is 8. And this turns out to be 8 times e to the 8x. Now, some of you, as I mentioned before, might notice this looks awfully similar to our little rule that d over dx of e to the kx is equal to k times e to the kx. And this is actually where that rule comes from, and what makes this rule possible is the chain rule. Now, moving on, let's try an example with the natural log ln of x. So say we are given y is equal to ln 3x plus 5. What is the inside and what is the outside? So for this question, the inside will be this 3x plus 5, and the outside will be the ln, like we saw in our first problem of 2x plus 4 to the power of 500. Similar concept. So let's write what our f of u is. It is ln of u. And I guess a good way to remember this is that the f of u will always be something that you are plugging something else into. Like in this case, we are plugging 3x plus 5 into ln, and with our exponential example, we are plugging 8x into e of x. And so that's just a good way to remember, or how to differentiate between the inside and the outside of these chain problem questions. And so our g of x is the inside, which is 3x plus 5. Now, let's find the derivative of f of u and the derivative of g of x. These are basically just following our previous rules where we saw that d over dx of ln of x is equal to 1 over x. Again, this time we just replace the x's with u's, same thing. So our derivative will be 1 over u. And now g of x, we see a constant, which we can forget about because derivative of a constant is 0. And 3 of x will end up being 3 times 1, since x to the first power minus 1 is x of 0, which is equal to 1. So our g of x will just be equal to 3. And now, to plug this into our equation, f of g of x times g prime of x is 1 over our original g of x, which is 3x plus 5, times g prime of x, which is 3. And to simplify this, we just pop this 3 into the numerator, since it is just another way of writing 3x plus 5 times 3 over 1, which is equal to 3 over 3x plus 5. And we stop here because we actually cannot simplify this. Even though some may notice we have a 3 in our numerator and 3 in the denominator, but we cannot simplify that as this 3 of x is being added with a plus 5, which means it's not independent. And therefore, we cannot cancel out those 3's. I also thought we could cancel at first, but I learned otherwise the hard way. So this is how we find the derivative using the natural log. And again, this is similar to our rule from earlier, where we saw that the derivative of ln to g of x is equal to g prime of x over g of x. See, because our g of x was 3x plus 5, and we found that the derivative of that is 3, and it matches our answer. Now, moving on, let's see a trigonometric example using the chain rule. So let's say we're given y is equal to sine 9x. At first, someone may see the sine x and remember that we said that the derivative of sine x is equal to cosine x. And while this will come in handy later, this does not take into account the fact that we have a constant involved with our problem, which is the 9. And as it is in the inside of the sine function, you cannot simply take it out and put it in front as you would with certain other problems. So again, we just need to define our inside and our outside, or well, I probably should have said outside and inside, since f of u is our outside and g of x is our inside. So to define our outside, we see that this is using sine of x, which is in our case sine of u. And the g of x is this 9x on the inside. Remember to include the x when writing the g of x, even though this is a sine function. The 9x is included on the inside as we change sine of x to sine of u. So the derivative of f to the u is cosine x, or cosine u, excuse me. As we saw in our little rule before, it comes in handy here. And g prime of x, again, 9 times 1 is equal to 9. So to plug this into our little function will be cosine of u, which is our g of x. So cosine of 9x times g prime of x, which is 9. And now, the reason I've been writing out our equation each and every time is because oftentimes people end up forgetting about this g prime of x. So I am writing it just to ensure we remember it and it sticks in our little brains. So now all we have to do is simplify, where this just becomes 9 cosine 9x. And that's it. That is the final answer for this problem. Now, what if we have the problem of a trigonometric function to a power? Say we're given y is equal to cosine 6x. Well, first, before we get into figuring the inside and the outside out, I should mention that cosine to the 6x can also be written as cosine x to the 6th power. So basically, the 6 being in the middle just means that it's the entire function being to the 6th power rather than just this little x inside. So knowing this, we could figure out that our f of u is equal to u of 6, as we have something inside being raised to a power, a function inside being raised to a power. And our g of x is equal to cosine x. And so f prime of u will be equal to 6u to the 5th power, using our power rule, n times x n minus 1. In this case, it would be 6 times u to the power of 6 minus 1, which is 5. And now, our g prime of x will be equal to negative sine x. Remember that all the trigonometric functions that start with a c turn negative once you take the derivative. So now, putting this into our equation, f prime of g of x times the derivative of g of x will be f prime of x, 6u, which turns into g of x, so 6 cosine x to the 5th power times our g of x, which is negative sine x. Now, this looks pretty complicated. However, the final answer will just be written as 6 cosine 5x sine x. I almost forgot the little negative in front. Remember to move the negative to the front. And this is our final answer for this problem. You could simplify more if you want, but oftentimes that ends up making it a bit more complicated. So we'll just leave it as negative 6 cosine to the 5th power of x sine x. So this concludes our lesson on the chain rule. I hope you all learned something new, and looking into the future, keep in mind that the chain rule is often used in combination with other rules, like as seen in this video, lots of times we ended up having to use the power rule within figuring out our chain rule. And it's also common to see the chain rule used within, say, product or quotient rule questions, which, if you haven't learned about already, you will learn about soon within your class. And I hope you have all a great day, and thank you for watching.